Hallo jongens, welkom bij deze nieuwe video over zwarte gaten. Ja, zwarte gaten hè. We gaan het hebben over wat een zwart gat nu eigenlijk is, hoe het ontstaat, de lagen en een singularity. Singularity is eigenlijk helemaal het laatste wat je zou zien als je helemaal door zou kunnen gaan in een zwart gat zonder dood te gaan. Dat lastig is. Oké, wat is een zwart gat nu precies? Een zwart gat is nu eigenlijk een ster wanneer hij ontploft en dan noemen ze dan een supernova. Dan wordt dat mega zwaar en wordt dat een zwart gat. Hoe ontstaat het zwart gat nu eigenlijk? Want eigenlijk had ik dat al een beetje uitgelegd, maar nu ga ik beter uitleggen. Een zwart gat ontstaat doorgaans wanneer een ster doodgaat en explodeert als supernova. Alle massa van de ster stort dan ineen, waardoor een zwart gat ontstaat. Iets wat Einstein met zijn relativiteitstheorie al voorspelde. Er komt dan zoveel massa samen in één klein puntje dat er een enorme sterke zwaartekracht ontstaan. Sorry, ik kon niet aan mijn woorden komen. Maar ja, dit is trouwens de eerste keer op mijn kanaal dat jullie mijn stem horen. Zometeen is mijn video, ik ga hier nog een video opzetten met dank aan Kurt Gezaagd in Nutshell. De lagen van een zwart gat bestaat uit een acredion disk, de event horizon, de iets dat ik niet kan uitspreken met jet, dat is die leen daar, een singularity, helemaal van binnen, een fotonsfeer en iets dat ik niet kan lezen. Maar vanaf de event horizon kan niks meer aan ontsnappen, zelfs het licht niet. En het licht is het snelste dat er bestaat. Dus dat is echt gek. Het licht gaat wel met meer dan 100.000 kilometer per seconde vooruit. Meer dan dat. Veel meer. Giovanni gaat er door naar de volgende. Bijna.
Black holes are one of the strangest things in existence. They don't seem to make any sense at all. Where do they come from? And what happens if you fall into one? Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star Or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the Sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course. What would happen to you if you fell into a black hole? The experience of time is different around black holes. From the outside, you seem to slow down as you approach the event horizon, so time passes slower for you. At some point, you would appear to freeze in time, slowly turn red, and disappear. While from your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of two things. 1. You die a quick death. A black hole curves space so much that once you cross the event horizon, there is only one possible direction. You can take this literally. Inside the event horizon, you can only go in one direction. It's like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated, at some point even tiny distances of a few centimeters would mean that gravity acts with millions of times more force on different parts of your body. Your cells get torn apart as your body stretches more and more until you're a hot stream of plasma, one atom wide. 2. You die a very quick death. Very soon after you cross the event horizon, you would hit a firewall and be terminated in an instant. Neither of these options are particularly pleasant. How soon you would die depends on the mass of the black hole. A smaller black hole would kill you before you even entered its event horizon, while you probably could travel inside a supermassive black hole for quite a while. As a rule of thumb, the further away from the singularity you are, the longer you live. Black holes come in different sizes. There are stellar mass black holes with a few times the mass of the Sun and the diameter of an asteroid. And then there are these supermassive black holes which are found at the heart of every galaxy and have been feeding for billions of years. Currently, the largest supermassive black hole known is S50014 plus 81, 40 billion times the mass of our Sun. It is 236.7 billion kilometers in diameter, which is 47 times the distance from the Sun to Pluto. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty, but filled with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of a black hole, one of the virtual particles will be drawn into the black hole and the other will escape and become a real particle. So the black hole is losing energy. This happens incredibly slowly at first and gets faster as the black hole becomes smaller. When it arrives at the mass of a large asteroid, it's radiating at room temperature. When it has the mass of a mountain, it radiates with about the heat of our Sun, and in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But this process is incredibly slow. The biggest black holes we know might take up to a googol years to evaporate. This is so long that when the last black hole radiates away, nobody will be around to witness it. The universe will have become uninhabitable long before then. This is not the end of our story. There are loads more interesting ideas about black holes. We'll explore them in part 2. A big thanks to Fraser Kane for help with this video. By the way, we've made some Kurzgesagt wallpapers in 4K for different screen sizes. You can get them on our Patreon page, which also helps us to make more videos. Like this December, the first month ever with 3 videos.
Oké, deze video is opgenomen door ABC Science. Is het toch van, hoe noemt het? Science ABC.
Known as Hawking radiation. Stephen Hawking was an English theoretical physicist and cosmologist who is most famously known for his theoretical prediction of Hawking radiation. That being said, what exactly is Hawking radiation? In order to understand this phenomenon, it's imperative to have a basic understanding of black holes. When a massive star dies, it leaves a small but dense remnant core in its wake. If the mass of that core is more than roughly 3 times the mass of our Sun, the force of gravity overwhelms all other forces and a black hole is formed. A black hole is not just empty space. In fact, it's a great deal of space packed into a very small area. Think of a star that is 10 times more massive than ours, being squeezed into a sphere with a diameter equal to the size of New York City. The result is a celestial object whose gravitational field is so strong that nothing, not even light, can escape it. This is how black holes earn their name, because they're pitch black. We have a separate video dedicated to black holes, which you can check out by clicking the link on the top right corner or visiting the link in this video's description. In the early days of scientific research concerning black holes, astronomers had a very basic understanding of them. It was believed that black holes radiated no energy of any kind. However, this all changed in the year 1974, when a young English physicist named Stephen Hawking came up with a theory proposing that black holes were not really black. In fact, he claimed that they could emit radiation. His theory stated that the mass of a black hole could become energy, which could then be radiated away. He formulated this theory by combining insights from quantum mechanics, the science of how the very smallest particles of the universe work, as well as Einstein's general theory of relativity, which deals with how gravity works at astronomically large scales. Not surprisingly, Hawking's theory was not initially well received in scientific circles. Even so, it gradually gained acceptance and popularity and became known as a groundbreaking discovery in the field of black holes. The radiation emitted by black holes was therefore named Hawking radiation, in honor of the physicist who predicted its existence. According to the principles of quantum mechanics, for every particle throughout the universe, there exists an antiparticle. These particles always exist in pairs and continually pop in and out of existence everywhere in the universe. Typically, these particles don't last long, because as soon as a particle and its antiparticle pop into existence, they annihilate each other and cease to exist almost immediately after their creation. That being said, things become a bit different at the boundary of a black hole's event horizon, the point beyond which nothing can escape its gravity. If a virtual particle pair blip into existence very close to the event horizon of a black hole, one of the particles could fall into the black hole, while the other could escape. The one that falls into the black hole effectively has negative energy, which is, in layman's terms, akin to subtracting energy from the black hole, or taking mass away from the black hole. The other particle of the pair that escapes the black hole has positive energy, and is referred to as Hawking radiation. Due to the presence of Hawking radiation, a black hole continues to lose mass and shrink until the point where it loses all its mass and eventually evaporates. It's not clearly established what an evaporating black hole would actually look like. The Hawking radiation itself would contain highly energetic particles, antiparticles, and gamma rays. Such radiation is invisible to the naked eye, so an evaporating black hole might not look like anything at all. It's also possible that Hawking radiation might power a hadronic fireball, which could degrade the radiation into gamma rays and particles of less extreme energy, which would make an evaporating black hole visible, and quite spectacular, as it breathes its last and ceases to exist in our universe. No matter what, it's best not to go anywhere near an evaporating black hole, as it would be a source of lethal gamma rays and energetic particles, even if you couldn't see anything. An evaporating black hole would be detectable from Earth only when it evaporated within the solar system, or close to a star near us. This is therefore a purely theoretical concept, and quite a complicated one to prove mathematically. But Stephen Hawking succeeded in figuring it out, and was the first person to do so. He was the first to set out a detailed theory of cosmology, explained by merging quantum mechanics and the general theory of relativity. Scientists and cosmologists still don't completely understand how quantum mechanics explains gravity, but Hawking radiation continues to inspire research and provide clues into the nature of gravity, as well as how it relates to other forces at work in our universe.
Bedankt voor het kijken en adios! Vergeet niet te abonneren en subscriben en duimpje omhoog.